things, okay, so one of the things that we get the most, or I get the most questions about and don't understand comments is the whole thing with Riemann sums. Look, we have done those Riemann sums. We have beat those examples to death on these Zoom lectures. Now, I'm happy to go over them again, but it's not fair to the rest of the class if we take class time to do that. The definition of the integral is difficult to learn, and it is going to require a great amount of effort on your part to learn it. And I'm happy to do that. I'm happy to schedule office hours with you to go over that. I just can't use class time to do it anymore. We've done, I mean, heck, we've integrated x squared by the definition. We've done it like 4 times in class now. So it's just, we just can't do it anymore. But that said, if you want to talk about those problems, and I'm really referring to homework, what, 11, I think, practice set 11. If you need to go over that, just send me an email and I'd be happy to schedule something with you. We can do it on a one-on-one Zoom meeting. So I hope you understand why I can't keep doing that in class, but I am happy to do it with you. Okay, so what we need to do is we need to talk about practice set 12. That's what we need to talk about today, because that's where we're at, and we have to try to keep pace with where we should be and where we're going. So
I have a question, right?
Yes.
So yesterday when I was doing practice at like sum of practice at 12, I came up with a situation where the cos goes with pi. Instead of cos x, it's cos pi. And when I tried to compute it in a calculator, I found -1 as the answer.
Because the cosine of pi is -1.
Yeah, and then I tried to plug in 3 and 2. And for 3 and 2, I get +1.
Well, why are you're plugging in 3 into the cosine?
Yeah.
What problem are you doing that? I don't even.
No, I was not plugging. I was just trying it for myself. Since pi is the same as 3.14, I tried to plug in 3 and 4, and I found +1. So I was wondering, why is it?
Well, the cosine of 3 should not be +1. I'm not sure. You're doing something incorrect. The only value of cosine that spits out 1, I mean, you got to look at the graph of cosine. Cosine is 1 when you plug in 0. It's 1 when you plug in 2 pi and 4 pi. And then when you plug in odd multiples of pi, like pi and 3 pi, you get -1. The cosine of like 3 is going to be some decimal value. It's not going to be a whole number. So you need to make sure your calculator's I don't know if you're in degrees or what you're doing. It's kind of hard for me to tell from this position. But if you're plugging cosine of, if you want to know the value of cosine of 3, you need a calculator. And the cosine of 3 is not going to be a whole number. You know, in fact, if you plug cosine of 3 into a calculator, you're going to get something like -0.98 or something like that. Does that make sense?
Yeah, it does.
Yeah. Okay, so let's look at some of these problems on practice set 12. Now, I don't want to do the same exact ones because that steals the fun from you, but let's look at some examples. So what we want to do today is we start with some examples using the FTC. So let me get another page here. So let's try to mimic so let's look at problems that are like number 1 on homework 12. So these are what we call indefinite integrals. So let's take something like 4x to the 5th plus x to the 2/3. So this is similar to 1A on the homework. I'd like to know what this this mathematical thing is. So when you have an integral sign and there are no bounds, notice there's no A or B, there's no numbers here. So what we do is we interpret this as what's called an indefinite integral. And an indefinite integral is very similar to what we called an antiderivative. And so what we need to do to finish this problem is we need to reverse the process of differentiation. Now, I mentioned last week that we wrote down a list of common antiderivatives just because we know our derivatives. So let's use this little metaphor analogy that I've said before, whatever you want to call it. I mean, if I say Shobit is younger than Ryan, that is a true statement in English. And then I can say the equivalent statement. I can say the equivalent statement is Ryan is older than Shobit. I'm using one sentence, I'm using younger, and in the other sentence, I'm using older, but I'm stating the same fact. And so that's how you need to think about these antiderivatives and derivatives. It's just two different ways to state the same fact. So how do I do this? Well, if I'm reversing the derivative, I write this as 4x to the 6th over 6th plus x. Now, the 2/3 plus 1 becomes 5/3 over 5/3. And then I have to write this arbitrary constant plus c. And of course, I can simplify this if I'd like. This is 2/3 x to the 6th plus 3/5 x to the 5/3 plus c. And the observation for you to make is that if you take your answer and compute its derivative, you get what you started with. So just for this one time, we will check this. If I take the derivative of my quote-unquote answer, what's the derivative? I get 12x to the 5th over 3 plus 3/5 times 5/3 x to the 2/3 plus 0. So it clearly checks. Does anybody have a question about this or a comment? Okay. Let's do another one. So let's do, how about we do the log of t plus 6t to the 3rd plus pi dt. To do this one, you have to just know that the antiderivative of log is, excuse me, erase this for a second. This is incorrect. That's not what we want to do. I'm getting ahead of myself. What I wanted was 1 over t plus 3t squared plus pi. And by the way, it should be noted that there's a slight typo in the homework. It's not a typo, but we don't know how to do it yet. So there's a typo in number 1, E. So use 1 over U instead of log U. And same with 2E. So hopefully you understand what I'm saying there. Does anybody have a question about that? Okay, so if I integrate this, I know that this is the log.
I just have a question about
Yes.
that.
What's up?
So for 2e, right? Then you're saying I did try and I did some. I looked up some sites on Google, and I found that I'm not sure if I'm true, but I found that the derivative of log t is the same as t log t minus t.
Well, not the derivative, the integral, yes. But
Yeah, the integral.
yeah,
Is
but
it that?
it's correct, but we don't learn that until next semester.
Okay.
It's not an easy, it's a much more difficult integral.
So, because I already did for number 2e and 1e, so do you want me to just leave it how it is?
That's fine. Yeah, sure.
Okay.
Yeah. But I won't ask you that on the test. I won't ask you the integral of log on the test. So.
Okay.
Well, at least not in this form. That's a mistake on my part. I'll fix that and I'll update the homework. But you don't have to redo it if you don't want to. And then this becomes t cubed over 3. So the 3's cancel. And then this becomes plus pi times t plus c. So pi is a constant. So its antiderivative is pi times the variable. Does anybody have a question about this? All right, now let's do these same problems, only let's just do them with bounds now, so we can compare with problem 2 on the homework. So let's integrate 0 to 2. So what problem did we integrate before? We integrated 4x to the 5th and then the 2/3. So now this guy, the difference between this guy and the previous 2 exercises is those practice problems were indefinite integrals. And when you're computing or determining an indefinite integral, you expect as your answer, your quote unquote answer, to be a function. That's what this is. But now we expect to get a numerical value. And how do we get our numerical value? We write down the antiderivative, which in this case was 2/3 x to the 6th, plus, when I added 1 to 2/3, I got 5/3. So when I divided by that, you get 3/5 x to the 5/3. And you are taking this thing and you are evaluating it at 0 and you're evaluating it at 2, and you're going to take the difference. So when I plug 2 in, I have 2 times 64 over 3 plus 3/5 times 2 to the 5/3. And then that's minus what happens when I plug in 0, which is 0, 0. Now, so now the problem is no longer calculus. This is a middle school math problem. It's arithmetic, only you have some exponents. Now, I've said this since day one of this class. I would love and I expect exact values for your answers. So some of you will just go plug this into a calculator, and that's not what I want. I want the exact value. You could say that I'm being picky or I'm being technical, but I'd like the exact value. And so the exact value of this is what? Well, 64 times 2 is 128. And that's over 3. And what's this other number? What is 2 raised to the 5/3? Well, that's the same as 32. You take the cubed root of 32. So there's a few ways that you can think about this. Either way, you know, you need to be able to, you know, again, maybe some of you just don't have, you know, you just don't want to do it the long way. And I guess that's fine. That's absolutely your call. But 2 to the 5/3 is the same as, again, it's the same thing as 2 to the 5th is 32. So you really want the cubed root of 32. So one way that you could write this is you can write this as follows. You can write it as 2 times 2 to the 2/3 or 2 to the 5/3, however you want to write it. Or you can leave it like this. Does anybody have a question about that?
For some of my answers, I didn't know what to do, so I kept some of them as decimals.
Well, I mean, okay, that again, I would prefer, so going forward, you should write your things as exact values.
I mean, I can still go and change, I guess.
I don't care if you change it now. I'm not going to take points off of you right now.
Okay.
But for example, on the final, I'm expecting exact values. And look, the reason for that is real clear. One of the things that we need to understand, particularly some of you who are going to go into certain fields of study, you have to understand the difference between an exact value and an approximate value. It's a super important thing. And so, you know, that's just one of my philosophies. It's important. And so that's what I'm going to ask you to do. So this is an ugly looking answer, but it is an answer. Does anybody have a question about this? All right, sweet. So let's go and do the next one. What was it, 1 over t? So now let's do this. It was 1 over t, and then what was it, 3t squared plus pi. And let's integrate this from, say, 1 to e. Okay, so we saw on the previous slide that the antiderivative is log of t plus t cubed plus pi t, and we're evaluating this between 1 and e. So when I plug in e, I get log of e plus e cubed plus pi times e. And then that's minus log of 1 plus 1 cubed plus pi times 1. So let's just remind you of what's happening here. This is when t is equal to pi, or excuse me, e, and this is when t is equal to 1. And so what is the log of e? You guys should know that it's 1, and this is 1 plus e cubed plus pi times e, which we'll write pi e. And then this is minus, log of 1 is 0, plus 1 plus pi. And so you can clean this up rather nicely. The ones will cancel. So this is e to the cubed, or e to the third power, plus, and you could write this as pi, and then it's e minus 1, if you'd like. That's one way to write the answer.
How about the integral of e power 3x? What will that be?
Of which one?
E to the power 3x.
Okay, we'll do that in a second. Let's finish this one up first. Do we have any questions about this one?
No.
Okay. All right, so you said e to the 3x. Well, let's do that one. Let's do another example. So let's say we wanted to integrate from, say, how about 1 to 4 of e to the 3x dx. How's that? Well, what's the antiderivative? The antiderivative is 1/3 e to the 3x. Now you might say, how did I get that? Well, it's the rule. It's what it is. And if you don't see that, take the right-hand side and take the derivative. Look, some of these things you just have to know. And I don't mean that you're born knowing them. I mean you know them because you reason them. You say, oh, that's right. I know how to differentiate the right-hand side. I know that the derivative of e to the 3x is 3e to the 3x. And so that makes that formula correct. You just have to know them. Just like when you're driving down the road and you see a stop sign, you know what to do. You weren't born knowing that a stop sign means stop. You learned it. Just like you have to learn what these antiderivatives are. And so then you just plug in 4. So you get 1/3 e to the 12 minus 1/3 e to the 3, which you might want to just write as maybe you just factor out the 1/3. Right like that. Does anybody have a question about this? Comment. All right. So that's how you do problems 1 and 2. You have to know the antiderivatives. And as I said, 1 and 2e, or there's a typo, I'll fix that. And then we'll move forward. Okay. So now let's look at using the other part of the fundamental theorem. So compare these guys with number 3. So here's what you need to note or recall. The FTC Part 1 says the following. It says that if you have an integral where the bottom bound is a number and the top bound varies, then the derivative of this integral is just the function that you're actually integrating. So this is a, look, this is a bunch of symbols to you right now. It's hieroglyphics. It makes no sense. And that's okay. That's because your brains are normal. Those are advanced symbols that represent difficult concepts. But if we think about what this mathematical statement says in just layman's terms, in baby terms, this says, look, what do we do in math? We always work from the inside out, right? This says that if you integrate something, then you differentiate it, you get what you started with. It says that integration and differentiation are inverse processes. They undo each other. So, for example, if I wanted to differentiate this integral, say from -3 to x of, how about -4t to the 5th dt, the fundamental theorem of calculus says this is just equal to -4x to the 5th. It literally says you take t, and wherever you see a t, replace it with x. That's what it's saying. Now, if you want to have a deeper understanding of this, you need to think about those area functions we studied last week. This is not an easy concept. It requires a great deal of effort to truly understand. Now, you have a choice. You can truly understand what's happening, or you could just see what I did there. I took x and I replaced it, or I took t and replaced it with x. Let's look at another example that's quite similar. My pen is acting up. So similarly, let's take something like the derivative of this integral. How about 1 to x of, let's use u this time. How about u to the 15th cosine of u squared du? This just becomes x to the 15th cosine of x squared. That's it. No plus c, no number, that's it. Does anybody have a question about these two examples?
So you just replace the value that's there with x.
Well, only, okay, yeah, but you got to be careful. That's only true when the bottom bound is a number and the upper bound is x. If you look at C and D on the homework, you'll see that ain't the case. So you have to rewrite them first. And we're going to get to that now.
I still don't get what you meant. If the lower bound is...
Hey, again, so look, we call this is the upper bound. You see where my pen's moving?
Yeah.
Upper bound, lower bound.
Okay.
Upper bound, lower bound. The lower bound must be a number. And again,
for that to happen.
Yes.
Okay.
Notice here it's -3. There's nothing special about -3. It does nothing for the problem. I could have written anything here, 0, pi, anything. Same thing on the next one. I put 1 there, but it doesn't matter what it is. doesn't matter as long
No,
as it's
not
a
really.
number. Now, if the upper bound is a variable, then as you suggested, all you do is you replace this letter here, U, with X. But that only works, only works when you have number downstairs, variable upstairs. So if you look at something like C, that's not what you have. So you have to modify it first. You have to rewrite. So if I had something like the derivative, and now my lower bound is the variable, and say my upper bound is a fixed number, now it doesn't apply directly. I have to rewrite it. I have to say, oh, okay, I have to get it in the right form. So how do I get it in the right form? I have to put a minus sign in front of it. Now, of course, you're going to say, why? Well, we talked about that last week. If you flip the bounds, if you flip your bounds, your lower becomes upper and vice versa, then you put a minus sign in front. And then now the FTC applies, and you can just switch T and X. So there is a subtlety.
Okay, so the value becomes negative, and if it's a minus from before, it becomes positive, right?
You mean out front?
Yeah, like if let's say d of dx will be like minus the lower bound and the upper bound sign, and then that function, and then when you change the function, it will become a positive, right? That's what I mean.
When you say change the function, what do you mean? Do you mean flip the bounds?
What I basically mean is like you see the first equation you wrote over there. What if you put a minus sign in front of it?
Okay, then if I put a minus, then minus times a minus would be plus. So
Okay, that's what I.
okay, now the fun begins. Now, in something like D, the big difference is that the upper bound is a function of X. Notice if you look at homework 3D, upstairs is a function of X. It's not X, it's X squared. Well, what does the chain rule says? Well, the chain rule says the following. So let's do the problem in general. Suppose you have your number downstairs, but upstairs you have some function of X. So now you have to really jump up in your difficulty level. The chain rule says you take the derivative of the outside, which is just f evaluated at the inside, times the derivative of the inside. So if we apply this reasoning to the problem similar to say 3D, if I wanted to differentiate something like this, 0 to x, say, cubed, of, let's just say, the sine of t dt, the chain rule says that this is the sine of x cubed times 3x squared. So this is a little more involved. Does anybody have question or comment? Look, one of the things that we'll find, and I've seen this pattern all the years I've been teaching calculus, which is quite some time. Problems like 3 are much more difficult for students to grasp than problems like 1 and 2. 1 and 2 will typically get answered correctly on exams. Most students will mess up problems like 3. It's just the way it is. Questions? Comments, concerns? All right, so I'll let you think about number 4. Don't want to give away that fun. Does anybody else have a specific question about problems 1, 2, or 3? Going once, going twice. All right, so
So for such equations, you actually find the derivative of the function.
for number 3,
Yeah.
yeah, you're finding a derivative. Absolutely.
No,
Those
like
functions,
for
those
the
are
last one.
functions defined as integrals, which is a completely legal thing to do, and it's actually done oftentimes in the higher up you go in math, the more likely you are to see functions that are defined as integrals. It's extremely common. Does that answer your question? Or
Yeah, it does. So for that part, right? The last thing, the one we are saying right now. So you only find the derivative of the inside, something that's inside the sign, right?
No. See, again, what you're looking for, Shobit, is you're just trying to memorize a pattern here, and that's fine. You're trying to recognize that I'm replacing one letter with another letter, and that's okay to do. But what you're doing is you're confusing the bigger picture, though. The bigger picture is in problem 3. I have 4 functions written, and I want you to compute the derivative of those 4 functions.
I get that, but what I mean is like over there you wrote f into g of x, right?
Yes,
Multiplied by g, derivative of g. So what I meant is you only find the derivative of the second function, right?
that's correct. Oh, yeah. Okay, you're talking about me.
Yeah, I was talking about that.
Right. Okay. Yeah, that's correct. So this formula that I have written here that you're talking about, I am using 2 big things here. I'm applying the chain rule to the fundamental theorem of calculus. And so you are correct. The derivative, so the function whose derivative I'm actually applying is, a more clean way of seeing this is if I'm calling, if you want to compare it to the actual chain rule. Let me call capital F of x this integral. I don't want to use g here. I want to use if I call this is the function and I'm composing it. So the function that I'm after is actually f evaluated at g, which now becomes this. So really, you could think of little f down here of g of x. That's just the derivative. So note that f prime is just little f of x. Now, I don't know if that makes it easier to see or if that confuses you more, but you can think of it that way as well. Look, the learning curve for this is steep. It just is. This is not, this material is not learned in a 5-minute attempt. It's more often learned in many, many 20 and 30-minute attempts. It's just, it's hard to learn this stuff. Does anybody else have a question about this? Comments?
Can we do another example just like for the chain rule? Can you give another
Yeah,
example?
sure.
Yep.
So let's say now I had something like this. So let's suppose I wanted to take this creature. Well, the chain rule says it's the cosine of 1, and then you replace t with whatever's upstairs. And then it's times the derivative of whatever was upstairs, whatever was in the upper bound, which is this 16x. So again, you'll see there's a simple pattern here, but the reason the pattern is simple is a much deeper thing. Don't confuse the t's and the x's. This is a t right here, albeit it's wrong.
Shouldn't it be 1 over 16x?
No, why? What's the derivative of ax squared?
Ax.
8x squared. What's its derivative? 16.
16, yeah.
The first thing you do is replace t with whatever the upper bound is, and then you multiply by the upper bound. Does anybody have a question? All right. So let's move on briefly. Okay, so next topic, more applications. Of the integral. So we already saw one application. And that was area. So our next one is what's called average value.
Okay, I just want to go back a bit like on the top part. So you replace first the t with 8x squared. That's when you find the derivative over there.
Yeah, I replace the t with 8x squared, and then I multiply that whole thing by the derivative, which is 16x.
So when you say prime of g, you mean actually the upper bound, right?
That's correct, yes.
Okay, I thought you were finding the derivative of the inside function.
No. I'm finding the derivative of the upper bound. If you go back to the previous page, you'll see that the upper bound is some function of x.
Yeah.
So I'm calling it g because I don't know what it is in general.
That's why I was
Yeah,
confused.
in this problem down here, the g is x cubed. On the problem on the next page, g is 8x squared. So I'm taking the derivative of the upper bound.
Yeah, it makes sense.
All right, so our next application of the integral is what's called average value, which is important in many applications. It is a generalization of the mean. So average value of f of x on some interval, is a generalization of what we call of the average that you're familiar with. So you guys have all done this before. What is the average? So suppose you have numbers, say x1, x2, all the way up to x sub n. The average, or as you guys may have heard, the mean, is what? Well, the mean is you add them all up, and then you divide by how many there are. Now, of course, we're adults now, so we can write this in summation notation to make it look real cute, if you will. So if you want, you can write this as 1 over n times the sum of x of k, k goes from 1 to n. So there's no doubt in my mind that you guys computed averages in your life. You may have not have written the definition this way, but every one of you has added up 4 numbers and divided by 4. Every one of you has added up 7 numbers and divided by 7. It's one of the first applications they teach you when you're in, like, secondary school learning arithmetic. Okay, so, what we'd like to do is generalize this. If we have a function, well, a function has infinitely many values if it's continuous. And so it doesn't make sense to define its average value this way. So how could we figure out the average of a value? The average value of some continuous function? So here we go. If f of x is continuous, or even just bounded on AB, we define its average value as f with a bar over it, and then you take the length of the interval and you multiply it by the actual value of the integral. So let's do an example real quick to see how this works. So let's compute f bar for f of x equals x squared on 0, 1. So f bar would be 1 over 1 minus 0 times the integral from 0 to 1 of x squared dx, which we can just compute as 1/3. We've done that integral a handful of times now. So average value has lots of different places it shows up. Many of you will see it in places like probability and statistics, physics, engineering. Does anybody have a question about this? Maybe you're building something and you have, maybe you have steel bars or wires, and you might want to know the average temperature along a wire, or the average current along something. One of the things you'll find out if you take certain physics classes or certain math classes, engineering, is you'll find out the way to answer that stuff is through integration. Fun times. Does anybody have a question? Okay, so another application which we can cover briefly is motion along a line. So we've already discussed this before. So we already saw let's use S of t. And remember, the operative word here is displacement. So if we have an object moving along a line, and it has a displacement of S of t, then what is its velocity? Its velocity is the derivative. And what is its acceleration? Its acceleration is the derivative of velocity. Okay, so that's written in the language of derivatives. What we'd like to do now is we would like to write these things not in the language of derivatives, but in the language of integrals. So what does this mean in terms of integrals? So Well, using the fundamental theorem of calculus, we can rewrite in terms of integrals. So if you're trying to connect some dots here, I told you on homework 3 we often write functions as integrals, and here's a prime example of that. S of t is always equal to s of 0 plus the integral velocity. And then similarly, your velocity at any time is always equal to your initial velocity plus the integral of your acceleration. So this is your initial position. This is your initial velocity. So what we're saying is, if I give you an object's acceleration, you can determine its velocity. And then once you've determined its velocity, you can determine its position. And it's a very amazing fact that if you know, and it's amazing yet it's not. It seems like it's common sense. What these equations are saying is if you know how an object is moving, which speed it's moving, you can predict where it's going to be at any given time. Does anybody have a question or a comment? All right. There's other applications we can write down right now, but we're going to wait because the problem is as we're soon going to find that integration is not as easy as taking derivatives. And so the first thing we have to do is learn how to integrate more functions before we can do some applications. And so that's what we're going to do on Thursday. Does anybody have a question?
No.
Comments, concerns? All right, so sweet. So work on this homework. If you have any questions, specific ones, let me know. And if you want to schedule any office hours via Zoom, I'd be happy to do that. If you send me an email and I don't respond before the end of the day, send it again, please. That way, in case I missed it, which is very common, I get tons and tons of emails, and I don't want to miss out on helping you guys out. So if you guys don't have any questions, I'll stop this now.